Morning, all of you. Acid and bases. Arrhenius concepts of acid and bases. Arrhenius, a Swedish chemist, was the first to define acid and bases in aqueous solutions. According to Arrhenius, an acid is defined as a substance which contains hydrogen and which, when dissolved in water, gives hydrogen ions. According all mineral acids like HCl, HNO3 and H2SO4 containing hydrogen when dissolved in water dissociate completely into hydrogen ions. Arrhenius named these acids which dissociate completely in water as strong acids. There are other acids like acetic acid, carbonic acid and phosphoric acid which when dissolved in water do not dissociate completely into ions. As a result, an equilibrium is set up between the ions and the undissociated acid molecules. Arrhenius names these acids are as weak acids. According to Arrhenius, a base is a substance which contains hydroxyl group and which when dissolved in water give hydroxyl ions. The substance like NaOH and KOH which when dissolved in water dissociate completely to give hydroxyl ions. Arrhenius named these bases which dissociate completely in water as strong bases. There are substances which do not completely dissociate into hydroxide ion. Arrhenius named these substances as weak bases. For example, substances like NH4OH, MgOH2 or AlOH3 do not dissociate completely to give OH ions. Hydrogen ions obtained from the acid and hydroxyl ion obtained from the bases combine together to form unionized water. Arrhenius described this combination of H positive and OH negative ions as neutralization reaction. Example, NaOH gives Na positive plus OH negative and HCl gives H positive plus Cl negative. Combining these equations, Na positive plus OH negative plus H positive plus Cl negative gives Na positive plus Cl negative plus H2O. Arrhenius concept is very simple to apply and explain a number of phenomena like neutralization, hydrolysis of salt, strength of acids and bases. However, there are certain limitations which are described below. Arrhenius concept of acid and base is applicable only in aqueous solution. This concept fails to explain the acid or base behavior of substance in non-aqueous medium such as liquid ammonia, sulfur dioxide, alcohol, etc. Arrhenius concept fails to explain the acidic character of substances like CO2, SO2 and SO3 etc. and basic character of substances like NH3, Na2CO3, CaO etc. Arrhenius concept also fails to explain the reaction between an acid and a base in the absence of water. Although the Arrhenius concepts of acid and base suffers from a number of limitations, yet the concept is very useful and informative for an elementary approach. Bronsted-Lowry concept. Arrhenius concept of acid and bases was further improved by Bronsted and Lowry. Both Bronsted and Lowry in 1923 incidentally introduced the same definition for acid and bases. According to Bronsted-Lowry concept, an acid is a substance which can donate a proton, whereas a base is a substance which can accept a proton. In other words, an acid is a proton donor whereas a base is a proton acceptor. As a result, Lowry-Bronsted concept is sometimes called proton donor acceptor concept. According to Bronsted-Lowry, a neutralization reaction involves the release of proton by an acid and the acceptance of the proton by a base. For example, the reaction between HCl and NH3 to form the salt ammonium chloride can be represented as NH3 plus HCl gives NH4 positive plus Cl negative. The curved show how electron must rearrange to result in the transfer of hydrogen atom from the acid to a base. The unshaded pair of electrons on the nitrogen of ammonia is attracted by the partial positive charge on hydrogen atom in the polar hydrogen chloride molecule. A comparison of these structures of the reactants and products shows that the hydrogen atom which was bonded to chlorine in the reactants is bonded to nitrogen in the product. Thus, a proton has been transferred from chlorine to nitrogen to act as a Bronsted Lowry base, a species must have at least one unshared pair of valence electrons so that it can form a covalent bond to the proton to act as Bronsted Lowry acid. A species must contain at least one hydrogen atom that is attached to an atom that is more electronegative than hydrogen. In this case, HCl loses a proton and is an acid. Ammonia accepts a proton from HCl and is a base. It is important to note in the above examples that water acts as a base with respect to hydrochloric acid and sulfuric acid. Interestingly, water acts as an acid with respect to ammonia. Such a substance which acts as both acid and base is called amphoteric or amphoteric substances. Similarly, bicarbonate ion behaves as an acid or a base. Other example of amphoteric substance is hydrogen sulfate ion, conjugate acid-base pairs. HCl being an acid donates a proton from Cl ion, whereas ammonia being a base accepts a proton and form ammonium ion. Now the chloride ion has a tendency to accept the proton, whereas ammonium ion has a tendency to donate a proton. In other words, an acid donate the proton becomes a base, and a base accepts a proton and becomes an acid. Thus, a base formed from the acid is regarded as the conjugate base of the acid. Similarly, the base formed from a base acid formed from a base is called conjugate acid of the base. In the example above, between HCl and NH3, Cl negative is the conjugate base of HCl. Acid and bases, they are related by the loss or gain of H positive ion, are called conjugate acid base pairs. A strong acid has a weak conjugate base and vice versa. Some other example of conjugate acid base are cited below. HNO3 plus H2O gives H3O positive, NO3 negative. HCN plus H2O gives H3O positive plus Cn negative. Here H3O positive and H2O are conjugate pair, acid and base, and HCN or Cn negative is also conjugate pair, acid 1 and base 2. It is further important to note the Bronsted-Lowry concept is not restricted to only neutral molecules. This concept is equally applicable to ions as well. A careful inspection of the above discussion reveals that a substance is capable of showing acidic character only if the other substance is capable of accepting the proton. That is a base. For example, HCl is an acid in aqueous medium because water can accept the proton from HCl. However, HCl is not acid in benzene because benzene does not accept H positive ion from HCl. Second, do not neutral molecules but cations and anions may act as acid or bases. Third, both Arrhenius and Bronsted-Lowry concept require an acid to be source of proton. Thus, all Arrhenius acids are Bronsted-Lowry acids. According to Arrhenius, a base is a substance which gives OH negative in the solutions, whereas according to Bronsted-Lowry concept, a base is a substance which can accept a proton. Carbonate ion can't give OH negative in aqueous solution, but therefore it can't be a Arrhenius acid, Arrhenius base. Thus, all Bronsted-Lowry bases are not Arrhenius bases. Limitations of Bronsted-Lowry concept. Although Bronsted-Lowry concept could explain the shortcomings of Arrhenius concept, yet it could not answer some of the well-established reactions. The reactions between acidic oxides like CO2, SO2 and SO3 with the basic oxides like CO, BaO and MgO, which takes place even in the absence of water. The acidic nature of compounds like BF3, FeCl3, and AlCl3. Lewis concept of acid and bases. G. N. Lewis in 1923 proposed a more general definition of acid and bases, which is based upon the donation of acceptance of electron pair. According to Lewis concept, an acid is the substance which can accept a pair of electrons. A base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor. It means that a substance which has vacant orbitals to accommodate one or more pairs of electron can act as Lewis acid. On the other hand, a base is an electron pair donor. It means that any substance with unshared pair of electron can behave as a Lewis base. Thus, the acid-base or neutralization reaction involves the formation of coordinate bond between the electron pair donor and the electron pair acceptor. For example, the reaction between boron trifluoride BF3 and ammonia is a typical Lewis-based acid-base reaction. Let us now discuss in detail. According to this concept, Lewis acids are classified as molecules having central atom with incomplete octet of electron. Boron trifluoride, aluminium trichloride, etc. are the acids of this type. Second, simple cations. All the cations are short of electrons and can behave as Lewis acid. Large-sized cations like Na positive, K positive, Ca2 positive, and Ba2 positive, etc. behave as weak Lewis acids. This is because these have little tendency to accept electrons. On the other hand, small-sized cations such as H positive, Ag positive, Li positive ions have a strong tendency to accept the pair of electrons and are strong Lewis acid. In addition, highly charged cations have a higher tendency to accept electron pairs relative to lower charged cations of the given metal. Third, molecules in which the central atom has available d orbitals and may acquire more than 8 electrons. Compounds such as AlCl3, SiF4, SnCl4, SbF5 and SO3 are Lewis acids. Fourth, molecules with a multiple bond between atoms of dissimilar electronegativities. Carbon dioxide represents an interesting example of a double bond between carbon and more electronegative oxygen atom. Oxygen, being more electronegative, has a tendency to attract the shared pair of electron more towards in CO2. As a result, it acquires positive charge on the carbon atom and becomes electron deficient and attaches with the oxygen of the hydroxide ion. Lewis base. According to this concept, Lewis base may be classified as one of the following types of the substance. Combination of stannic chloride with ethers to give an adduct. Lewis acid-base concept discussed above is widely used because of its simplicity in understanding of many acid-base reactions. In spite of its wider applications than Arrhenius and Bronsted-Lowry concept has several disadvantages which are discussed below. Lewis concept is too general and consider all reaction forming a coordinate bond to be an acid and base reaction. This is, however, not true always. According to Lewis concept, some of the transition metals that form compound with carbon monoxide such as NiCO4 etc. are acid-base reaction, which is not correct. Formation of coordinate bond between an acid and a base is the basis of Lewis concept. However, the well-known acids like HCl, HNO3 and H2SO4 do not form any coordinate bond with the bases such as NaOH or KOH. Accordingly, HCl, HNO3 and H2SO4 should be regarded as acids according to Lewis concept. Lewis concept does not give any uniform scale of acid and base strength. Lux-Flood concept of acid and bases. A new concept of acid and base was proposed in Lux in 1939. The concept was further extended by Flood. According to Lux-Flood concept, acid is any substance which accepts an oxide ion, whereas a base is a substance which gives an oxide ion. According to Lux-Flood theory, bases can be represented as base gives acid plus O2 negative and acid gives base plus O2 negative. According to Lux-Flood concept, substances that show a tendency to lose as well as gain an oxide ion as termed as amphoteric. Zinc oxide represented an interesting example of amphoteric character. For example, zinc oxide can lose O2 negative to form Zn2 positive. In addition to zinc oxide gaining an O2 negative to form Zn2 negative. Similarly, Al2O3 can behave both as an acid and as well as base. This concept of flux flood is very useful at high temperature, especially in glass ceramic industry and metallurgical operations. The concept of flux flood can also be extended to halides and sulfides. Solvent system concept. The solvent system concept of acids and bases was postulated by Cady Isley in 1928. It is an extension to the Lowry-Brunsteit concept and it is applicable to both protonic as well as non-protonic solvents. According to this concept, an acid is a substance which either by direct dissociation or by interaction with the solvent gives a cationic character of solvent. A base is a substance which either by direct dissociation or by interaction with the solvent gives the anionic characteristic of the solvent. The characteristics cations and anions of the solvent are the ions produced during the autoionization. The prefix auto means itself. To illustrate this concept, let us consider the autoionization of some protonic and non-protonic solvents. Acid plus base gives acid plus base. H2O plus H2O gives H3O positive plus OH negative. H2SO4 plus H2SO4 gives H3SO4 positive plus HSO4 negative. For example, HCl is an acid in water solvent and it gives the cationic characteristics of water. Similarly, NH3 acts as a base in water as it gives the anionic characteristics of water. It is important to note the acetic acid behaves as an acid in water and is produced the cationic characteristic of water. Acetic acid behaves as base in sulfuric acid as it produces the anionic characteristics of the solvent sulfuric acid. Urea dissolves very readily in water and gives neutral solution. However, urea dissolves in liquid ammonia and behaves as an acid because it gives the cationic characteristics of solvent ammonia. Similarly to Arrhenius concept, neutralization reaction may be represented as the combination of cationic characteristics of the solvent with the anionic characteristics of the solvent to form the solvent or molecule. Some neutralization reactions are acid plus base gives salt plus solvent. NH4Cl plus NaNH2 gives NaCl plus 2NH3. Types of solvents. Solvents are classified in a number of ways on the basis of their physical and chemical properties. Broadly, there are three ways in which solvent can be classified. First, protonic and aprotic solvent. Solvents which contain hydrogen and can lose hydrogen in the form of proton are called protonic solvent. Example, NH3, H2S and HF. Solvents from which hydrogen can't be obtained in the form of proton are called aprotic solvents. Example, H3CN, C6H6. Acid base, acidic, basic and amphoteric solvents. Solvents which have a strong tendency to give protons are called acidic solvents. Common acidic solvents are H2SO4, HF, CH3, COOH, etc. Solvents which have a strong affinity for protons are called basic solvents like NH3 and 2H4 pyridine. Solvents which display both acidic and basic property are called amphoteric solvents. Example, water, methyl alcohol. Third, ionizing and non-ionizing solvents. Solvents which undergo self-photonization are called ionizing solvents. Example, hydrogen fluoride, sulfur dioxide. Solvents which do not ionize are called non-ionizing solvents. Example, carbon tetrachloride, C6H6. Effects of solvents on the acid strength, called leveling effect. The strength of an acid or a base depends largely on the nature of solvent used for its dissolution. Let us consider the dissolution of hydrogen chloride in three different solvents, that is ammonia, water, sulfuric acid. one can clearly see that HOClO is a strong bronzed acid in NH3, a weak base in water, and a strong base in H2SO4. The acidity and basicity of protonic solvent plays an important role in choosing of solvent for a chemical reaction. The strongest acid which is available in protonic solvent is that which results from the self-ionization of the solvent. Likewise, the strongest base available is that which results from the self-ionization of the solvents. Let us consider example. 2H2O gives H3O positive plus OH negative. In aqueous solution, the strongest acid which can exist and which can be available for the reaction is the hydronium ion. It means all the strong acids known to the chemist appear to have exactly equal strength in the aqueous solution. This results from the fact that acids such as perchloric, hydrochloric, hydrobromic, nitric, and hydrochloric acid are stronger proton donors than the hydronium ion. It means that acids stronger than H3O positive are level to the strength of H2O positive when placed in aqueous solution. In other words, water levels all the strong acids, namely HClO4, Hi, HABr, HNO3, and HCl to give the strength of H3O positive. Similarly, the very strong bases such as hydride ion, amide ion, and ethoxide ion all react completely in aqueous solution to yield hydroxide ion. It means that all these strong bases are labeled to the strength of OH negative ions on reaction with water. In other words, solvent water levels all these strong bases to the strength of OH ions. For example, when sodium hydride is added to water, a vigorous reaction occurs with a brisk evolution of hydrogen gas, and resulting solution is found to be the solution of sodium hydroxide. In order to compare the relative strength of acids, strong acids and bases, the selection of the solvent is very important. The solvent selected should be such that it ionizes the strong acids and bases of different extent. Such a solvent which ionizes the acid and base to different extents is called a differentiating solvent. Acetic acid can be used as a differentiating solvent because strong acids like HClO4, HiHBr will ionize to different extents in acetic acid. Acetic acid is a poor proton acceptor. Perchloric acid reacts completely, whereas other acids do not react completely because of incomplete protonation of acetic acid by these acids. On the basis of relative strength of different ionization of these acids are HClO4 greater than Hi, then HBr, then HCl, then H2SO4, then HNO3. Acetic acid is a leveling solvent towards base such as Cl negative, OH negative. This is because acetic acid reacts with the base and level them to the strength of acetate ion. However, strongly basic solvents such as liquid ammonia acts as differentiating solvents towards bases. Thus, it may concluded that acidic solvents tend to differentiate between acids and level of bases, whereas basic solvents tend to differentiate between bases and level of acids.